Welcome to Project 3 in the course Advanced Methods for Data Analytics, CSDA 1040. Our project is about the forecasting of the Spanish electrical power generation grid for the coast and the load. We used the ARIMA and deep learning model from TensorFlow LSTM. So I will start just by giving a brief about the power generation field and why we need to do these predictions for the power generation and what factors are affecting the power generation. So um, there is two things that we are going to predict in this project, which is the cost and the load. And both of them are related, of course. So the loads are all the consumers from factories, from homes, anything that consumes electrical power is and connected to the electrical grid, as you see here in this picture, is considered a load, and it's affecting by several things. For example, such as the weather. The weather conditions and the temperatures outside affects the load because you need heating, you need cooling. This is one of the major loads for consumers, either for facilities, companies, or for homes. Then there is the normal loads like light, any appliance, and then there is industrial loads that runs 24/7, maybe runs 12 hours a day, maybe run 5 days a week, 24 hours. It depends on the type of the factory and the loads connected. For the generation, we have several sources of generations. It depends where you are or where we are in the world or what type of generation. There is clean and there's a conventional, which is like the thermal power stations, which uses coal or uses gas or uses oil for generation. There is the hydro with its type, either wave or dams. There is the solar and there is the wind. Some of these, of course, are affected with the weather conditions also, like solar and wind and tidal power stations. And some does not affect it, like the nuclear power plants. The thermal has some effect due to the efficiency of the plant and the cooling requirements. It depends which country or which area you are in. I'll talk briefly also about the electrical bills and how it's calculated so we can understand how the cost of the power is also calculated. The electrical bills usually at any country consists of two parts. One is variable and one is fixed. The variable is affected usually by the fuel charges and the prices, by the source of generation. For example, if it is a clean energy or not, and how much is the cost for the generation, how much is the cost for operation from different plant to another. All these factors affects the cost. There is some fixed price, which is the base of the electrical services, like the transmission charges or the base cost for generation. These two items affects the bill. So since the electrical generation is controlled by private sectors, mostly in different countries, so there is like a sort of bidding every 24 hours, every 12 hours on the cost. Like the government will buy the power generated by the plants, and each plant will give the cost he want to sell his power at, and then the government will choose if they are going to buy at this cost or at this rate or not. When we looked at Spain, we found that the Spain grid is distributed into several sources: 20% coal, 18% from gas, 10% from oil, 21% nuclear, 18% wind, and there is solar biomass, which is 3%, and hydro is 10%. The data set which we choose reflects these numbers, and this we will see in the graphs when we do the analysis. Our analysis is done using 5 data sets. The first one is for the generation. It contains data about all about the loads and the generation from each type of plant on hourly basis, and it contains also the price per day and a prediction done for the price a day ahead. Then we have another data set for the weather conditions in the major 5 cities of Spain. It's also hourly values. Then we did a search on the internet, and we could get data for oil prices. It's also hourly, natural gas prices, and coal prices, and then the exchange rate between US dollar and euros, because the prices here is in euros. We will try to predict the load using simple ARIMA method, and then we will try to predict the cost using a multivariate using TensorFlow, LSTM, to predict the cost. We'll move forward to how we did the prediction for the 2 target variables. So quickly, this is we imported the data set. The data set contains a lot of information. We had to go through them. I will not go through all the cleaning, but I will show this curve, which is important. This graph shows the total load, and then this is the generation from each type of plants. And as you see, if I can zoom on this graph, we will see that the major items, as we saw on the distribution, is we have the nuclear, which is almost stable, and this is related to the way the nuclear plants is operated. They don't usually fluctuate within the power. They have a base load, and they stay on this base load as long as it is required. They don't fluctuate, and then the government will ask the other producers to fluctuate, such as the producers of the thermal power generation, to achieve the required load, which they predict or anticipate at this certain day. And also due to the weather conditions, which is affecting the wind and the solar production, then the thermal plants will cover this production for the other plants, and this is clearly shown here with the data we have. This is again the same distribution. It shows which sources are generating more power. Then we have the weather conditions. We went through them and we distributed them across cities, and we built like a data set for each city. When we looked at the weather, we anticipated that, or from my knowledge of this domain and the generation, what is mainly affecting, or what I anticipate is affecting the forecast will be the temperature, the hourly temperature, the humidity, and of course the rain, and we have the cloudy conditions. So I included this, and I dropped several variables from this data set to be able to do the forecasting. We move to the ARIMA model. This is other data sets. So this is the oil prices from 2008 to 2020. And then we have the natural gas prices from 2008 to 2020. We have also the coal prices, which is an average, a monthly average, but we filled the hourly values with the same monthly average to be able to use it. And then we have the exchange rate. We combined all the data sets we have. Uh, and this is a graph showing the price for the generation with the other prices of the gas and average prices of the oil, natural gas, coal. So we started the ARIMA model by looking at the decomposition graph and see how the load is fluctuating and what are the parameters. And it seems that the load is stable, it's almost stable. We don't see a stationary load, so it's not increasing or decreasing, it's not changing over time, it's just fluctuating across the same mean value. And then we looked at the autocorrelation and the partial correlation, and we believe the model will be a good fit for this data set. So then we use the AD Fuller test to see the stationary, to see if we need to do any differencing on this data set or no. And the p-value was 0, so this means we don't need to do any operations on this data set. We try to find the constants, the p and d and q for the ARIMA method. We use two ways to do this, and we got them. This is a diagnostic curve of the ARIMA, and then we were able to do the prediction, and the errors. Of course, if we look at the errors, the numbers are huge, but this is compared to thousands, 20,000, for example, here. So the MAPE is 0.07, which shows that the prediction has a good potential. Of course, it could be improved using different methods, and but this was a simple one just for testing. Then we moved to the forecasting of the cost using the TensorFlow LSTM model. So we did the same. We checked the stationary for the target variable, the cost, and we then looked at the correlation with all the variables within the data set, either the weather conditions across the 5 cities or the generation from each source. What we anticipated is we will have the coal and the natural gas generation has highly effect, and also the weather, the prices for the coal and the prices of the price of the natural gas will have a high effect on the cost of the megawatt. We also did a model using the XGBoost to get the power of prediction for each variable, and this is the feature importance graph that is showing the humidity at Valencia is important than the total load, actual, the cool price, the generation, fossil gas, the wind speed, humidity at Barcelona, generation hydro water reservoir. We looked at both the correlation and the feature importance, and we selected the features that we think that it will do best within the prediction. Then, since we had a prediction already included or a forecast included within the data set, we calculated the root mean square for this forecast, and it was 12.34. Then we moved with the TensorFlow LSTM, following the steps for this. We scaled the value. We scaled all the data set to be able to have less time for the prediction and better prediction. Then we calculated. We were trying to calculate the learning rate, and it was um, we got the value for the learning rate, and we put it in the model for the prediction. We run the model, and this is the graphs for, since this is the most important graph, this is showing the prediction against the actual value, and the error, the root mean square error is 2.20, is 2.257, which is a good value. So this is mainly the two models we used in this generation. We had some anticipations when we before doing the correlation and before running the models, and I think this like this expectations was correct. We are trying to build an app using the same model for predicting of the cost. We are facing some issues, but once we finalize these problems, we'll deploy the app to Heroku. Thanks for your time and for listening for this analysis.